let's begin our discussion on how to get the inverse Laplace transform of some function f of s by applying the Heaviside method of partial fraction decomposition, and then using the inverse Laplace transform of the factors that are found. So if f of s is the rational function whose inverse Laplace transform we're trying to find, then the first thing we have to do is to rewrite the function according to its poles. That is, we need to find the roots of the denominator, and those roots are minus p1, minus p2, all the way to minus pn. It has to be n because of this n here. So the denominator is rewritten as s plus p1 times s plus p2 times s plus pn, and the denominator doesn't need to be changed. We can copy it right here. Okay, that allows us to assume, and this is where the Heaviside method begins, to assume that this is equal to certain sum of factors. This is r1 over s plus p1 plus r2 over s plus p2 plus all the rest of factors plus rn over s plus pn. This is called the residue, and its residue is associated to one pole. Each pole has its residue, and the Heaviside method is actually designed to give us the values of each one of those residues. So Heaviside's idea is very simple but powerful. If we are saying that this is the same as this, we can write everything here. We say that f of s is equal to r1 over s plus p1. I'll leave some space here and write r2 over s plus p2. Some space, dots, rn over s plus pn. And now let me copy this because I'll need it twice. Copy. So if we multiply both sides of the equation by s plus p1, I have to multiply all of them by s plus p1, s plus p1, s plus p1. And now we assume that s is equal to minus p1. That is, if we particularize each one of these functions at s equal to minus p1, s equal to minus p1, s equal to minus p1, what do we get here? Well, here s plus p1 cancels out with this denominator and we get r1, and here we have minus p1 plus p1, that is 0, and all this is 0, and the same thing happens with pn. Everything is 0 and everything else is 0, so on the right side we only have r1. So this is kind of a formula for r1, although I don't like to learn this through formulas. So let's do the same with s plus p2, s plus p2, s plus p2, s plus p2, and then we force s to be equal to minus p2. S is equal to minus p2. S equal to minus p2 with all of them. S equal to minus p2 and s equal to minus p2. Again, here minus p2 plus p2 is 0, so all this factor is 0. Here s plus p2 cancels out and we get s2, and all the rest of factors are again 0. So here is the formula for R2. So let's apply this in an actual example, a simple one. We have the function f of s given by s plus 1 over s plus 2 times s plus 3, and we want to find what its inverse Laplace transform is. So we already have this in written in a way that we know its poles. We don't need to calculate them, so we can directly assume that this is equal to the first residue over s plus 2 plus the second residue over s plus 3. Let me copy this once, twice. So to get R1, we'll multiply everything by s plus 2, s plus 2, s plus 2, and assume that s is equal to minus 2. I'll write it just once. So here this goes with this goes with this, and all this goes to 0, leaving only R1 on the right hand side. So R1 is equal to minus 2 plus 1 over minus 2 plus 3, minus 2 plus 3, and that's equal to minus 1. The second one, we multiply everything by s plus 3, s plus 3, s plus 3. Particularization. This goes with this, leaving R2 alone. This is 0. This goes with this, and R2 is equal to minus 3 plus 1 over minus 3 plus 2, which is equal to minus 2 over minus 1, that is to say 2. So we can replace R1 and R2 by their values, minus 1 and 2, and therefore if we apply the inverse Laplace transform table, or the Laplace transform table, because it works both ways, f of t is minus 1. The residue works as the a parameter when we found the exponential functions Laplace transform. Minus 1 is a times e to the minus 2t. The pole goes with t in the exponential. Plus 2 is a times e to the minus 3t. This is our inverse Laplace transform. Let's go with a second example, a little tougher, given by f of s is equal to 2s plus 1 over s squared plus 2s plus 1. Well, the difficulty here comes from the fact that the roots of the denominator are complex numbers. So there are different ways to deal with that situation, and depending on the book that you look at, well, there are several explanations. I've chosen the one I like the most, which is just apply the same thing we did in the simpler previous case. R1 over S plus 1 plus J. This is one of the poles. One of the poles is minus 1 minus J, plus R2 over S plus 1 minus J. So if we do the same as before, we find that R1 is equal to, well, again, we would have to multiply both sides by this term here, and then assume that S is equal to minus 1 minus J. So what we have here is 2S plus 1 over S plus 1 plus J times S plus 1 minus J, all that by S plus 1 plus J. This goes with this, and this is evaluated at S equal to minus 1 minus J, leaving minus 2 minus 2J plus 1 in the numerator, and minus 1 minus J plus 1 minus J in the denominator. This goes with this, and this is equal to minus 1 minus 2J over minus 2J. But we don't like J's in the denominator, so we multiply by J both the numerator and the denominator, and here we have minus J minus 2J squared, which is plus 2, over minus 2J squared, which is plus 2. And finally, this is written as 1 plus J halves. Okay, we could do the same to find R2, but I won't do it because I know that it has to be the complex conjugate of R1. That is to say, 1 minus J over 2. But if I were, I don't know, taking an exam, I would do it just to check that all my operations are okay. So if we have the residues, we have everything. We can rewrite f of s according to them, and that is f of s is equal to 1 plus J over 2 over S plus 1 plus J, plus 1 minus J over 2 over S plus 1 minus J. And now we go to the Laplace transform table, and it's exactly the same as in the other example. F of t is equal to, this is multiplying 1 plus J halves, the exponential, and the pole is here, minus 1 plus J times t. Just in the other example with real numbers. Plus 1 minus j halves times e to the minus 1 minus j times t. But the thing here, this is not a very neat way to express a function of time, because remember that here we're in the real domain and we don't like to have j's in the real domain. But that's not a big deal, because we can work a little bit with this expression, as I'll show you right now. We have to expand it. Here I have e to the minus 1 plus jt plus, I'll take this multiplication and then this multiplication, e to the minus 1 minus jt plus g over 2, this one times this one, e to the minus 1 plus jt, and this times this one, minus j over 2 times e to the minus 1 minus j t. Let's continue. This is equal to e to the minus t times e to the minus j t plus e to the minus t times e to the plus j t plus, common factor here, j halves, e to the minus t, e to the minus jt minus e to the minus t, e to the plus jt. And as you see, e to the minus t is in all these factors, so we can take it out. And this is equal to e to the minus t, we're close to the end, times e to the minus jt plus e to the jt plus j over 2 e to the minus t times e to the minus jt minus e to the jt. Okay, now remember the Euler formula. The Euler formula tells us that this is 2 cosine of t, and it also tells us that this is 2j sine of t. So this 2 goes with this 2, and this j times this j turns it into a minus 1 here, so that the final result is e to the minus t times 2 cosine of t minus the sine of t, the inverse Laplace transform of this f of s.